Today we're going to talk about graphs of polynomial equations. So a function of the form f of x is a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus dot 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 plus a sub 1 x to the first plus a sub 0. And this dot 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 just means that there could be a bunch of stuff in there. That is a polynomial function of degree n. It's degree n because n is the biggest power in the polynomial, not because it's the first term. So I could switch these terms around all I want, but if that's the biggest power, that's still going to be the degree. Okay, and this a sub n will be the leading coefficient because the leading coefficient always goes with the biggest power. Now we've graphed functions of degree 0, which are horizontal lines. We've graphed things of degree 1, which are non-horizontal lines, and degree 2, which are parabolas. Okay, so they look kind of like this. Anything that looks like f of x equals a. So that would be like f of x equals 2. That's degree 0 because it's x to the 2x to the 0 power. Remember, x to the 0 power is 1, and 1 times 2 is 2, so it's just 2. That would be a horizontal line, f2. We can do things that look like f of x equals 1/2 x plus 3. Okay, that is degree 1 because my biggest power of x is 1. That's a line with a slope of a. In this case, it has a slope of 1/2. I can do f of x equals, 3x squared minus 5x plus 7. Okay, that's degree 2 because the biggest power is 2. And that's a parabola. Okay, it's going to be some U-shaped thing. Okay, so we're going to talk about features of graphs of polynomial functions. So the graph of a polynomial function is continuous. They're always continuous. That means that you can graph the entire thing without picking up your pencil. Okay, so if I had a function that looked like, something that looked like this, that would not be continuous because I had to pick up my pencil to get past this vertical asymptote right here. Okay, so polynomials, you can always draw the entire thing start to finish without picking up your pencil. So something like that. Okay, that's continuous. Okay, they're smooth. Graphs are always smooth in polynomials, so that means there's no sharp edges or cusps. So what that means is I don't have anything that looks like this. I don't have sharp edges like this. I don't have a cusp. A cusp looks something like this. Okay, I don't have any of those things. All right. It's a function of degree n. A function of degree n has at most n minus 1 turns. So if I have a parabola, that's going to be degree 2. A parabola has 1 turn. It'd be 2 minus 1. A cubic, so something to the 3rd power, can look like something like this. Okay, it's degree 3. It has 2 turns. 1, 2. Something to the 4th power might look something like this. Okay, it has 1, 2, 3 turns. There's always one less turn. Now, it can have less than that, but it can have at most n minus 1 turns. Whoops. Okay, if the leading coefficient is positive, then the graph of the graph rises from left to right. Okay, so it would do something like this. The graph would either do something like this. Whoops, gotta have a pen, right? It would do something like this, where it's rising from left to right. Okay, or it would do something like this. Okay, now it does decrease a little bit right here, but it's increasing again to the right. If it's negative, it will fall from left to right. So this would be a negative power. Okay, this would also be a negative power. So these are negative powers over here. I'm sorry, they're, yeah, the leading coefficient is negative, not negative powers. The leading coefficient. So my leading coefficient is negative over here, and over here, my leading coefficient is positive. Okay, moving right along. So here I have some different functions. Here I have a cubic, okay, negative 1/3 x to the third plus x minus 1. Okay, you can see I can draw the entire thing without picking up my pencil. So it's continuous. It's smooth. It doesn't have any sharp corners. It's got nice smooth corners. It's got, it falls, because it's negative, it falls from left to right. Okay, so those are all properties that I can see here. Now here, I have g of x is 3x to the fourth plus 4x to the third. So again, though, it's a polynomial, so it's smooth, it's continuous, it's degree 4, so it has 1, 2, 3 turns. Okay, could have less than that, it might have only 1 turn. And it rises as I go to the right, so it drops down here a little bit, but as I go further and further to the right, that thing's rising. Okay, whereas this was falling to the right. Okay, over here, x to the fifth. Okay, my degree is 5. It can have at most 4 turns. There's 1, 2, 3, 4. These are a little sharper, but they're not sharp. They're smooth. You're not going to cut yourself by running your hand across that thing. It rises to the right. Okay? And so you get an idea, you can get an idea of what a polynomial is going to look like just from seeing the degree and the leading coefficient. Okay, monomial graphs are graphs that only have one term, so they're f of x equals a sub n x to the n. Now, if n is an even number, so this would be things like x to the second, x to the fourth, x to the sixth, you get u-shapes, okay? Now, we've done x squared before. It's a nice parabola that touches right there at 0, 0. Okay, it's nice smooth. It's continuous. Now, x to the fourth is very much like it. The x to the fourth is the red one here. It's smooth and continuous. It's a U-shape, but look at the difference. Outside of -1 and +1, it's steeper than the green one, okay? But along between -1 and +1, it's flatter, okay? And then you go to x to the sixth, that's the blue one. That is even steeper outside of -1 and +1, but in between -1 and +1, it's flatter across the bottom. So those are all U-shapes. Now, if you add other terms, you know, like if I added minus 5x to the fifth plus x to the fourth, you know, that kind of stuff in between there, what that will do is that will change that U-shape and possibly make it bumpier, okay? Have more turns. Okay, odd functions, same thing, except they look kind of like this, okay? Even functions are going to look like this or like this. Odd functions are going to look like this or like this. But it's the same rule. Outside of -1 and +1, as a power gets bigger, it gets steeper. So here's x to the third is the green, x to the fifth is the red, x to the seventh is the blue. Okay, but inside, it gets flatter and flatter. So here's my green. It's hard to see in this, but the red is a little flatter than that, and the blue is even flatter than that. If you look at the notes, you'll see it. Okay, now, what do different things do, transformations? Well, you can have a negative leading coefficient. That just takes a figure and flips it upside down. So in this case, I've got x squared as the green one here, and if I make it negative x squared, it just flips it upside down. Okay? Over here, this is x cubed, is the green one. It goes like this, and negative x cubed just takes the green one and flips it upside down, so it now goes like this. Okay. Moving equations up and down. I can do that by simply adding a number or subtracting a number from the end of the equation. So here I've got x cubed, right here, the green one. And if I take x cubed plus 3, that just takes all the answers and adds 3. So it takes 0 and moves it up to 3, and it takes, 1 and moves it up to 4, and so on. So it just moves this figure up 3 positions. If I want to move it down, I can subtract something from the end of the equation. So here's my x cubed, and this time I have x cubed minus 5, so it moves everything down 5. Okay, if I want to move things side to side, I can add a number inside the function. So here I have an x squared, okay? And then look what I did here. I took x plus 4 inside the parentheses squared. That moved it to the left 4. Just took that whole thing and shifted it to the left. Now, be very careful because people often think that since it's plus, it's going to move it to the right, and it doesn't. It moves it to the left. Okay? It's the opposite of what you think. So over here, the green one is x squared again, okay, but x minus 2 inside the parentheses shifts it 2 to the right. And then I can do combinations. I could take this and I could add 4, and that would just take this one and move it up 4. Okay, graph the polynomial function x cubed minus 9x. Okay, so this would be easy to do on a table. Okay, I might start with 0. So that would be 0 cubed minus 9 times 0 would be 0. So 0, 0, that's the origin, that's our friend right there. Okay, and 1, that would be 1 minus 9, so that's going to be negative 8. 1, 2, 3, 4, 5, 6, 7, 8. It's going to be right here. I think 2 is going to go off the graph. Okay, if I put 2 in there, I would get 8 minus 18. Oh, well, I guess that would still be other. That would be negative 10. So that's going to be right here. What if I put 3 in there? That would give me 27 minus 27. That's going to give me 0. Well, look at that. This thing curves back to 0 right here. If I put in 4, 4 cubed would be 64 minus 36. What is that, 28? So that's going to go off the graph. So over here, this thing's going to go like that. Now what's going to happen the other way? If I plug in negative 1, I'm going to get negative 1 cubed is negative 1 plus 9. That's going to be 8. Okay, so 1, 2, 3, 4, 5, 6, 7, 8. It's going to go here. Negative 2. Let's see, negative 2 would be negative 8 plus 18. So that's going to be 10. Okay, so that's going to be right here. Looks like this thing's going to be symmetric maybe, huh? Negative 3 is going to give me negative 27 plus 27. It's going to give me 0 again. So this thing's coming back to here. Looks like it's going to be symmetric, so this thing's going to come up here like this, and it's going to take off way down there like that. Okay, so there's my graph. And I know I got all the terms because x to the third, degree 3, means it can have at most 2 terms. Well, there's one and there's the other one, so I know I got the whole graph. I know that since it's x cubed, it is going to rise to the right and go down to the left. Okay, and we call that left and right behavior, okay, which I think we'll talk about right here. Okay, so left and right behavior. The left and right behavior simply describes what happens to a function as you move to the left or the right of the function. So I've got a couple of funky equations here. Okay, so this one here in green, this one, the left behavior is x goes to infinity as x goes to infinity, so I'm going this way, y also goes to infinity. Okay? So as I go further and further this way, I go further and further that way. Now, as x goes to negative infinity, so now I'm going this direction, y still goes to infinity. Okay? Because it goes back up this way. So this is my left and right behavior for the green one. Now, the red one, over here, as x goes to infinity, so I go this way, where does y go? Y goes to negative infinity. It goes down. Okay? As x goes to negative infinity, so I'm going this way this time, what's happening to the graph? It's going up, so y goes to infinity. And this is the way we write left and right behaviors. Okay, so got a little assignment here for you. It's a couple pages. It's a bit of work, but I think you'll have no trouble with it. Have a great day.